Thanks very much. So thanks so much for the invitation to speak here. It's a great honor, and it's my great pleasure to give an introduction to my current area of research, which is called p-adic non-abelian Hodge theory. And okay, so to be honest with you, when I was a PhD student not too long ago, I found p-adic Hodge theory pretty scary. I mean, definitely intriguing, it seemed very powerful, but quite scary because I know it feels pretty vast, and then there's all these definitions of like period rings and this myriad of mysterious functors, and half of it is written in French, and I don't know. So if I had been to a conference and there was a talk on a non-abelian version of that thing, I probably wouldn't have had too high hopes for my Friday morning. But then later in life, I discovered that p-adic Hodge theory is actually really fun if you allow a little bit of complex geometry to explain what's going on. And then I discovered that the non-abelian version of that is even more exciting. And okay, so this is what I want to give you, okay, a little bit of an overview of doing this talk. And by way of motivation, let's start with what one could call a selective overview of arithmetic geometry. So let's start with a smooth variety over the rational numbers, maybe an elliptic curve like this one. And then if we have such a variety, we can pass to the complex numbers where we can maybe do geometry. Or in fact, let's start with considering the topological space associated to the C points of this variety with the Archimedean topology. So for example, if I started with this elliptic curve, then I would maybe get a donut. And somewhat surprisingly, the topology of this space knows already really interesting information about the arithmetic of this variety I start with, right? For example, by just saying something about the homology, by just counting the number of holes, I could learn something about the genus of my equation, and thereby about, for example, the number of rational solutions I can expect this equation to have, yeah, which is very interesting information, surprisingly extracted from this topological space. But I can also put myself in a different framework and consider X as a complex manifold. So maybe it has the same topological underlying topological space, but now instead, what I look at is the local structure of the space, which I identify with some subspace of the complex affine space. And then I can consider functions on this and can, okay, for example, consider analytic functions like exponential and logarithm, but I can also differentiate maybe from some partial derivatives or some total derivatives or some integrals and stuff like this, and play with that. And okay, this is also useful for arithmetic applications. For example, I could use this world of complex manifolds to talk about uniformization of my varieties. For example, if I have this elliptic curve, I could uniformize it as a complex torus, and then maybe talk, for example, about the periods or about moduli spaces or whatever. Okay, and of course, I can consider it simply as an algebraic variety. Okay, so I didn't really have an idea of what picture to put there. So okay, this is just a copy of Hartshorn. I mean, let's be real, that's what algebraic geometry feels like or looks like most of the days. Okay, and so there I also have these specific tools of this kind of area. For example, I could consider coherent sheaves on this algebraic variety. Or for example, consider the étale side and put the étale topology on X, which is of course also very important for arithmetic applications. And okay, so for numbers, like if I'm doing number theory, then like all of these worlds are kind of interesting, like different tools that I can choose. But of course, in arithmetics, we are not only interested in the Archimedean place, but also in the non-Archimedean ones. So I could instead consider also the base change to CP, where CP is the completion of an algebraic closure of QP, so the p-adic analog of the complex numbers. And okay, so of course, I could once again study algebraic varieties over this field. And okay, it turns out that essentially this is the same theory as I would get over C. The reason being that, okay, I can do something slightly confusing, namely choose an algebraic isomorphism between C and CP. So this tells me that even though that's a weird piece of data depending on the axiom of choice. Maybe this is, okay, the theory somehow knows the same about the variety. But I could also do something more analytic in flavor and pass to the analog of a complex manifold in the p-adic world, which is called a rigid analytic space, in the sense of Tate maybe, or okay, nowadays we also have other ways to think about it. And so this is a bit similar to, or yeah, really analogous to considering X as a complex manifold, in the sense that now I describe it locally as something which is cut out of some p-adic disk, which is maybe the correct analog of affine space in this context. And once again, this allows me to do analytic stuff, like exponentials, logarithms, for example, some kind of p-adic uniformization, for example, an elliptic curve. Okay, if I choose p appropriately, perhaps for this elliptic curve, I could write it as a Tate curve, which is some kind of analog of a complex torus. Okay, and then so maybe these were vaguely ordered chronologically. So we started in the 19th century, and then this is maybe the second half of the 20th century, and the most recent thing on my slide is the world of diamonds. Okay, this is somehow maybe 10 years old, introduced by Peter Scholze, some kind of p-adic world that I'm going to say a little bit more about during the talk, which I can put my variety in to learn interesting new things, and in particular do arithmetic with. Okay, so that's a very broad summary of a small part of arithmetic geometry. Of course, there's a lot missing, like the mod p picture and so on. Okay, but the idea is if we start with some equation, we can use all these different tools to study it. And in particular, one important way in order to extract arithmetic information is to talk about cohomology in these various different realms. Okay, and this brings us to the first question I want to talk about in the first part of the talk, namely, what is Hodge theory? And the answer is that it's about comparing cohomology theories in these different worlds on the left-hand side of the slide, so in complex geometry. Okay, so let's maybe start with, for example, if you like, the elliptic curve that was on the slide, or more generally, some smooth projective variety, which might have come from smooth projective variety over the rationals. Then associated to these various different worlds, there are several good cohomology theories for my variety. And the first thing I could do is to simply consider the topological space, and I get singular cohomology, also called Betti cohomology in algebraic geometry. Okay, and this is not supposed to teach anyone what singular cohomology is, but so just as a collective reminder of how it feels like, right, of the flavor of singular cohomology. So basically, it's about what the topological space looks like when I'm in I simplex, right? So I just test this topological space by simplices. So what I really see from this variety is just the topological structure, and I use this to define some complex, and then maybe there's some dualization going on because we consider cohomology instead of homology, and then I just take the cohomology of this complex. Okay, so once again, the details don't really matter right now. What I want to get at is that in the definition of this thing, I really only use the topology of the C points of this variety. Okay, and the next thing I could do is to put myself in this framework of complex manifolds. And then I would maybe arrive at the Ram cohomology. And this is what happens if I instead consider X not as a topological space, but as a differentiable manifold. Namely, okay, so once again, just very, very briefly, as a reminder of the flavor of this thing, so I consider in this world of differentiable manifolds, some notion of smooth differential forms, and then there's some exterior derivative, and then I've defined some complex, the de Ram complex, and then I take its cohomology, and this defines the Ram cohomology of this variety. Yeah? So this really was talking now about differential forms on X. And the third world I talked about on my first slide was the world of algebraic varieties. And this I can use to define the third kind of cohomology theory, which is Hodge cohomology. So how does this work? This time I consider X as an algebraic variety, let's say over the complex numbers. And in this world, we also have a notion of differentials. an algebraic notion, the Kähler differentials. And this time I consider them as a coherent sheaf on my smooth projective variety. And then we have this rule of sheaf cohomology that I can apply to coherent sheaves. And this I can use to define Hodge cohomology. So basically I need to incorporate both the cohomological degree of the sheaf cohomology and the order of the differentials. And then I define Hodge cohomology as this direct sum. Okay, so in particular, by definition, this Hodge cohomology has an interesting additional structure, namely a grading. Yeah? By definition, it is a direct sum of smaller things, functorially. Okay, and this was completely algebraic in nature. In particular, I can do the same thing later in the p-adic setting. I didn't use anything about the complex analytic structure of my variety. So we had these three different kinds of cohomology theories: singular about the topology of the space, de Rham about the differential structure, and Hodge, which just used algebra and coherent sheaves. And what Hodge theory is essentially about is that it tells you that these are all the same, yeah? Which is, okay, let's write this down slightly more precisely as a mathematical theorem. This is a theorem from the 30s due to Georges de Rham and William Hodge, which says that, okay, I'm really mixing two separate theorems here. There are natural isomorphisms between singular cohomology and de Rham cohomology, and then maybe I should say between singular cohomology and Hodge cohomology. And if you think about it, this is really surprising, right? We used very different information about the variety, but we can still, at least on the face of it, extract the same amount of data. Okay, maybe the Hodge cohomology also has a grading, and there's some additional structures, and at least leads to interesting structures like called Hodge structures and so on. But if we just care about the cohomology groups, then surprisingly, whether I consider as a topological space, a differentiable manifold, or an algebraic variety, these kinds of cohomology theories seem to know the same thing about the space. Okay, so just as a concrete example of what this might look like, if I now take an elliptic curve, then the associated complex manifold is a complex torus. And I can consider this as a topological uniformization as well, because C is the universal cover of this elliptic curve. So in particular, this tells me what the fundamental group, the topological fundamental group of X is, namely it's this lattice. And I can use this to compute the singular cohomology from this uniformization, namely it will be somehow the additive characters of this lattice, if you like, which is just the same as the dual of singular cohomology, of course, as always. Okay, and then that maybe at least gives some idea of what this Hodge decomposition looks like in this case, namely starting with the differential on this curve. These I can also describe explicitly, namely basically they all just come from the differentials on C, the universal cover. I take a class in the homology, which I interpret as a path, and then I just integrate the differential over this path. Okay, and the point is that there was some integral that appeared. Okay, so I used some kind of complex integration at some point. And this, in this case, really defines a part of this Hodge decomposition. Okay, and this Hodge decomposition really appears in number theory, for example, in the theory of modular forms, maybe in the context of the Eichler-Shimura isomorphism, for example, where I basically do Hodge theory for the modular curve and describe singular cohomology in terms of, well, some kind of Hodge cohomology which turns out to compute modular forms. Okay, so this was a brief tour of Hodge theory, and now we can say what p-adic Hodge theory is. Namely, p-adic Hodge theory is about comparing p-adic cohomology theories. So we are now on the right-hand side of this first slide, and we're in the realm of p-adic geometry, and think about maybe rigid analytic spaces and maybe even diamonds at some point. Okay, so what kind of p-adic cohomology theories do we have? Okay, so no worries, I'm not going to review them all. Okay, let's focus on two. And the setting for this is let's start with a smooth projective variety over QP, so that we're really in an arithmetic setting, which simplifies some things. And then we consider its base change to CP, the completion of an algebraic closure of QP, like on the first slide. And then in this context, there are several good cohomology theories for such p-adic varieties. And the first one, maybe also historically, the first one is étale cohomology, as defined by Grothendieck. And for this, okay, so we could work in the world of algebraic varieties actually, but okay, for this it's sometimes easier to work in an analytic category, so for rigid analytic spaces. This explains that in some sense it's very close to singular cohomology. Okay, and once again, this isn't supposed to teach anyone who hasn't seen it before the definition of étale cohomology, obviously. Yeah, this is just more supposed to be a reminder, but in some sense, we again consider a topological space associated to X, except that it's not a topological space, but a site, so a category with a topology. And the category consists of all the étale morphisms over X, which are some kind of algebraic analog of unramified maps over X in complex geometry. And then I define some notion of a cover, set theoretic cover essentially, which gives me the site, and then I can consider sheaves on the site, and I can in particular consider these constant sheaves associated to z modulo p to the nz. And now what I do is, okay, this is always slightly confusing, right? But somehow this étale site only sees finite information. So rather than actually defining sheaf cohomology on the nose, I need to do something slightly auxiliary. Namely, I define étale cohomology with CP coefficients to be the inverse limit of all these finite steps étale cohomologies. And then I tensor with CP. Okay, whatever, just a fact of life somehow that at least in this classical setting of étale cohomology, one needs to take such a limit. This is later explained by new sites like the pro-étale site and so on, whatever. And there's already an indication why this is actually more interesting for arithmetic applications than singular cohomology, because by virtue of this definition by base change, the variety X came equipped with a Galois action. And because the formation of this étale site and then this cohomology is completely functorial, it naturally inherits a Galois action. Okay, and this is for arithmetic applications probably the most important structure about étale cohomology that we use. In particular, if we talk about, for example, Galois representations coming from geometry, like maybe in James's talk on Wednesday, then we usually mean that we somehow find our Galois representation in such a cohomology group with this natural Galois action. Okay, that was étale cohomology. And then now comes the last cohomology theory that I want to talk about today, and then we have them all, okay? Which is maybe the one which probably, just least known among the 5 ones I talk about, and this is V cohomology, okay? And if you like, you could also instead take pro-étale cohomology, but this is somehow conceptually what explains that we're in the world of diamonds, okay? And I will explain more about this later, but okay, this is something defined by Scholze roughly 10 years ago, and let me just give you a flavor of the definition, and then I will explain later why it's good. Okay, so we consider X as a diamond. What does this mean? What it means is that instead of asking what X looks like when I'm a simplex, I ask what X looks like when I'm a perfectoid space. Okay? And it really doesn't matter for now what perfectoid spaces are. They are some huge, infinitely ramified p-adic objects. But whatever they are, they come up naturally, also in number theory, and I can consider all of them. So the site of all perfectoid spaces over X. So once again, instead of testing by simplices, I test by perfectoid spaces. I need to work in some p-adic category and consider the category of adic spaces to make sense of this. Okay, whatever. This site has a natural structure sheaf because perfectoid spaces have a structure sheaf. And then I can just define V cohomology of X to be the internal cohomology of this site. Okay, not very spectacular, this last definition, but somehow interestingly, these perfectoid spaces seem to know a lot about this variety we started with. Okay, so and of course, as I said, we can also put ourselves in the algebraic setup and just consider Hodge cohomology, like we did over C. Okay, so that means that in summary, I told you about 3 different cohomology theories: Hodge cohomology, which is just some kind of sheaf cohomology of the Keller differentials. Then there's étale cohomology, and there's V cohomology. And okay, I should mention that in p-adic Hodge theory there are many others. Okay, and I'm sorry if I didn't talk about your favorite cohomology theory today. There's maybe a list of some of them. You might have heard about prismatic cohomology a lot recently, whatever. Okay, but let's focus on these three. And then once again, p-adic Hodge theory, hence the name, says that these three, and okay, a couple of the others, all agree in the following sense. So this is a theorem that goes back to Tate in the 60s, and then there's work by a lot of people, Coleman, Fontaine, Niziol, Tsuji, and then, okay, this theorem here is maybe due to Faltings in the 90s. And then the V cohomology part is probably due to Scholze. And it says that there's natural isomorphisms between all three of these different cohomology theories, okay? And I want to point out that even if we are only interested in the first comparison, which is probably the one which comes up classically, already in Faltings' proof, the proof goes by essentially going through the third category. Faltings doesn't say perfectoid spaces yet, but he basically considers some kind of V cohomology. Okay, so in order to compare these first two cohomology theories, one really needs to go through this world of diamonds in some sense. And once again, this is something extremely useful, this time even more probably for number theory, because we have this additional Galois structure on everything, right? For example, I mentioned Eichler-Shimura earlier. There's a p-adic version of this, which also tells you something about Galois modules, and this would be a special case of this. Okay, and in order to illustrate this further, sorry, I wanted to give names to these isomorphisms. The first one is called the Hodge-Tate decomposition. Decomposition because Hodge cohomology was by definition this direct sum of coherent cohomology groups, and the other thing is, for whatever reason, called primitive comparison theorem. Okay, this article of Scholze proves like a bunch of different comparison isomorphisms, and this is supposed to be the easiest one, hence why he calls it the primitive comparison theorem. Okay, but okay, don't read too much into that name. It's not primitive. Quick, nice. Okay, so once again, let's do an example of an elliptic curve. So what does this Hodge decomposition tell me in this case? So okay, let's say x naught is an elliptic curve over QP, and then we take the base change, and then there's a Galois action on this thing. Okay, and this is really the setting of Tate in this famous article about p-divisible groups, in which more than one subject was started, one of them being p-adic Hodge theory. And what Tate proves is that there's a short exact sequence where in the middle I have the Tate module, what we now call the Tate module of X, tensored up to CP. And then he constructs a surjective morphism to the differentials of X. And the kernel turns out to be the Lie group. But I can really identify these different terms with étale cohomology in the middle. That's essentially what the Tate module is. I mean, okay, so up to some polarization, etc. And I'm not very careful about Galois actions here, but whatever. And if I combine the two outer terms, the first one is identified with this sheaf cohomology of the structure sheaf, and the last one is the differentials. If I combine them as a direct sum, then I get Hodge cohomology. And the point is that in this presence of Galois actions, I can argue that there's a canonical splitting of the short exact sequence. I mean, well, Tate argues. So the sequence is canonically split, and this gives me this isomorphism between étale cohomology on the one hand and Hodge cohomology on the other hand. Okay, so this maybe gives an idea of what this Hodge decomposition feels like. And okay, this is of course also something which one uses a lot, for example, in the context of, well, arithmetic of abelian varieties or Shimura varieties. Okay, so this was p-adic Hodge theory, just very briefly. Now let's get non-abelian. Okay, I promise this to be fun. So, okay, what is non-abelian Hodge theory? So this is fundamentally about comparing coefficients for cohomology. Okay, so we are generalizing the cohomology theories now, and don't only consider some constant coefficients, but more general things. It's actually not how it's usually explained in my experience in the complex world, but I find this perspective particularly useful for arithmetic applications. Okay, so let's get back to the complex setting. So we jump to the left-hand side of the first slide and talk about complex manifolds. But okay, we start with a smooth projective variety again. And then there were these three kinds of cohomology theories: singular, de Rham, and Hodge. And each of them has a kind of generalization using coefficients. Okay, let me first briefly explain this for singular cohomology. And the correct notion of coefficients for singular cohomology is that we can take cohomology with values in a local system. Okay, so what is a local system? It's a sheaf on this topological space, which is just locally a constant sheaf, locally of the form c to the n plus m n. Okay, and then, okay, I didn't want to give the definition. Okay, it's just something I can do. Okay, I can define singular cohomology with values in a local system by basically not taking C, but this sheaf L in the definition at some point. But one thing I want to recall about it, because it's interesting from the point of view of number theory, is that there's a different way of describing local systems in a less geometric and more representation theoretic way. Namely, sorry, yes, okay. So first I should mention that, of course, this is a generalization, because if I take the constant local system, then this recovers the earlier definition of singular cohomology. Okay. Okay. Now briefly comes the part about representation. So any local system becomes isomorphic on the topological universal. Sorry, becomes constant on the universal cover, and this allows me to attach to a local system what's called the monodromy representation, which basically remembers how the fundamental group acts on this trivialization. And okay, turns out that there's an equivalence between local systems and representations of the fundamental group with values in C. And the other direction is simply given by taking a representation, and then I send it to the constant local system on the universal cover and quotient out by some diagonal action. Okay, whatever. The reason I mentioned this is that a similar construction will later appear in the p-adic world, and this will motivate why perfectoid spaces appear. Okay, so this is why I put this on the slide, and for later reference. Okay, that's just a thing we can do in sort of classical algebraic topology. Okay, but for now, let's jump to the next cohomology theory, which is de Rham cohomology. What are coefficients for de Rham cohomology? Okay, the answer turns out to be, so basically what I want to do is I want to kind of write down a more general version of the de Rham complex. And the datum I need for this is a vector bundle with a flat connection. Okay. Okay, and very briefly what this is, so this is a complex analytic vector bundle on X as a complex manifold. And then there's some way to explain what differentiation means on this vector bundle in terms of this thing called a connection. Namely, this is supposed to be C-linear and satisfy the Leibniz rule, which I've written there. Okay, this is just, I don't know, basically evidencing that this thing is like a derivation. And then the flatness means something about, okay, that there's a way to explain what nabla squared means. Doesn't matter for this talk. But if I have this, I can define a generalization of the de Rham complex. Yeah, so I can, instead of the structure sheaf, use this vector bundle V, and then instead of the derivation that one usually has this exterior derivative, we take this nabla, this connection. Okay, and this gives me a way to define de Rham cohomology with coefficients in a vector bundle with a flat connection as just the cohomology of this complex. And once again, there's like a trivial vector bundle with connection, namely, well, like an identity object, if you like, which is just a structure sheaf with the usual derivative. Yeah, I mean, I'm in the setting of differential manifolds, so I can explain what differentiating functions mean, and that's what I mean here. And this recovers then de Rham cohomology. Okay, so this was really a generalization of de Rham cohomology. Okay, and third, there's a way to generalize Hodge cohomology. And for whatever reasons, as soon as you do that, you're not supposed to say Hodge anymore, but Dolbeau. Okay, and I'll not do that because that gets confusing for this talk. Okay, so I just wanted to mention it. Then the generalization of Hodge cohomology is called Dolbeau cohomology. Whatever, I'll call it Hodge cohomology. But anyway, the coefficient objects are called Higgs bundles. And what is a Higgs bundle? This is something that, for whatever reason, first appeared in physics, hence the name. And some article of Peter Higgs, the guy from the Higgs boson. Okay, it doesn't matter. What it is for us is it's an algebraic vector bundle. Yeah, we want to do something algebraic. This was the realm of algebraic varieties. And then there's an operator called a Higgs field. And okay, this might first look like a connection, but it's actually something easier. Namely, it's just OX linear. Yeah, it's really a nice morphism of coherent sheaves. No differentiation, no exterior derivatives or anything going on. And then there's some condition which looks a bit like a flatness condition. This theta wedge theta is 0, whatever that means. Well, what it means is that I can define a complex again, and this is now called the Dolbeau complex, and it's basically okay. Looks a bit like the de Rham complex, instead that except that I take the Higgs field instead of the of number instead of the connection. And anyway, so if I have this, then in algebraic geometry, we have a way to take cohomology of complexes, right? And maybe, okay, historically, this is called hypercohomology. So I just take the hypercohomology of this complex, okay? Which is just the cohomology in the derived word, if you want, of this complex. And this is Hodge cohomology with coefficients in the Higgs bundle. And once again, the point is that there's a kind of trivial Higgs bundle, or an identity object in the category of Higgs bundles with respect to the tensor structure. And this is the structure sheaf on X as an algebraic variety, together with Higgs field 0. So I can just set theta to 0, and it will satisfy trivially all these conditions there. And if I do this, then basically this complex has 0 transition maps, and then there's some spectral sequences and whatnot. And this tells me that in this case, I really compute Hodge cohomology. Okay, so this is just a generalization of Hodge cohomology, which, well, comes up in complex geometry, okay? And now, point is, once again, that I can somehow compare these different generalized cohomology theories. But before I can do so, I first need to match up the coefficients, right? So that I know what to compare, okay? And for simplicity, let me just say what this theorem is in the case of curves, because then the statement becomes slightly easier, but there's a version in higher dimension as well. And okay, once again, I'm basically mixing two different theorems. The one is more classical, the Riemann-Hilbert correspondence. And then much more recent, there's a bit which is called the Collette-Simpson correspondence from the 90s. And the first statement, that's the Riemann-Hilbert part, is that there's an equivalence of categories between the category of coefficients for singular cohomology and the category of coefficients for de Rham cohomology. Okay, I can match up local systems and vector bundles with flat connection in some way. Okay, that's cool. And then it turns out that these vector bundles with flat connection I can in turn match with this third category of coefficients, which are the Higgs bundles. Except that this time I need to be a little bit more careful. I don't get all the Higgs bundles. There's some conditions, some algebraic geometry conditions. Okay, it says semi-stable and of degree 0. Whatever. Okay. Just that there's an additional algebraic geometric condition that I need to put on the Higgs bundle, but then I can match all of these different categories of coefficients. Okay, and at least for the first functor, one can really explain easily what it is. So I just take a local system, and then I tensor it with a structure sheaf. And because of this local constancy of the local system, this will be a vector bundle. And then I can just define the connection by just taking the derivative of the functions and doing nothing on the local system. Okay, that's kind of easy. And then, okay, maybe the hard part is proving that this is an equivalence. And I absolutely cannot tell you how the Collette-Simpson correspondence works. Okay, this is hard in the sense of it's actually real analysis. Yeah, you do need to go through some harmonic metrics, and it doesn't mean anything to me as if I put my number theory hat on. Okay, but it's I don't know. It's a thing that you can do. And the point is, of course, now that I can use this to compare these generalized cohomology theories. Okay, so I can match up coefficients objects. Let's say we start with a local system, and then we take its associated vector bundle with connection and its associated Higgs bundle. And the point of the main theorem of non-abelian Hodge theory is that then I can match up the cohomologies again. Okay, so the singular cohomology with coefficients in this local system turns out to be the same as the de Rham cohomology with coefficients in the vector bundle with connection. Turns out to be the same as the Hodge cohomology with coefficients in this Higgs bundle. Okay, and maybe this might not look very number theoretic, but this is actually something which also comes up. For example, I mentioned Eichler-Shimura earlier. If you think about what you need to do if you want to not get the modular forms of weight 2, but of higher weight, then you actually need some kind of coefficients. And if you think about it, then it's actually a version of this thing on the modular curve. Okay, but I didn't want to give the details because I would get us slightly too far away. But let me mention one thing. So this is actually, now we get into recent research in complex geometry, and we are at the, I don't know, Journées, géométrie algébrique or whatever. So there's moduli spaces of these objects. And okay, one can compare these, and it's really interesting and a bit subtle. And I don't know, there's big names like the P equals W conjecture, or whatever, which are like ongoing research topics in complex geometry, which compare moduli spaces for these three different worlds. Okay, this was just a little bit of an aside. Nice. Okay, so that's what non-abelian Hodge theory is. And now you can probably guess what p-adic non-abelian Hodge theory is. And now we are finally we arrived at the title of the talk. And the answer is that it's about comparing coefficient systems for p-adic cohomology. Okay, and this is what I want to explain now. So we need coefficients for Hodge cohomology. We already know them. These were the Higgs bundles. And now we need coefficients for étale cohomology and for V cohomology. Okay, so let's jump back to the right-hand side of the first slide. So we're in the p-adic setting. We have a smooth projective variety over QP. We consider its base change to CP. So we're in a setting of p-adic geometry. And we want to understand what coefficients for p-adic cohomology theories are. And let's start with the étale world. Okay, and basically it turns out, so as I mentioned earlier, that étale was in some sense conceptually quite close to Betty. And okay, this conceptual analogy can be technically be more precise, made more precise by Artin comparison theorems, etc. But okay, so the definition is there was this additional complication that the definition of étale cohomology involved some inverse limit. Okay, and I will see the same here necessarily for the coefficients, which is why the correct notion of a local system in this context is that I first define sheaves Ln, which are locally isomorphic to OCP mod p to the n. There's like the CP version of Z mod p to the n. Okay, and then I basically take the inverse limit in some sense. And after inverting P, this thing is called a CP local system. So this is in some sense the most down-to-earth definition of a CP local system. Once again, there's also more modern approaches to this by working on some different sides, not the étale side, but some pro-étale side, where I can really just copy the definition from complex geometry. Okay. But maybe this is the one that one usually uses in practice. And once I have this, I can define étale cohomology in the same way as I did it before. So I take the étale cohomology of all these finite steps, of all these LNs, the things which are locally isomorphic to OCP mod p to the n, and then I take the inverse limit of these cohomologies and invert p. And that's the definition of étale cohomology with values in a local system, as it might appear, for example, in Eichler-Shimura comparison. And, oops, okay, I meant to say that, okay, of course, if you take the constant local system, then this would recover étale cohomology as we had it before. Okay, and by a slight detour, I want to talk about representations. Okay, so in singular cohomology, there was this fact that local systems can be equivalently understood in terms of representations, right? So in the complex world, C local systems can be matched with representations of the fundamental group on finite dimensional C vector spaces. And the way this worked is that I take a representation and then I basically send it to a descent datum for the constant local system on the universal cover. Okay, so this was, I take the universal cover and then the constant local system and then quotient out by some diagonal action. Okay, and one can ask if there's a similar construction in the p-adic world as well for p-adic local systems. Okay, and this is where the perfectoid spaces will appear now. Okay, and the result is that the same works in p-adic geometry, which kind of tells you that we've given the correct notion of CP local systems. Okay, and the statement is that CP local systems, as I defined them on the last slide, these inverse limits of objects, are in one-to-one correspondence with continuous representations of, okay, the replacement I have in this world of the topological fundamental group, which is the étale fundamental group, somehow the Galois group of the étale side, with on finite dimensional CP vector spaces. Okay, so there's a very interesting difference to the complex world in the sense that now my fundamental group is a profinite group because it's a Galois group. And so I don't only want to talk about representations, but I also want to talk about comparing the topology on both objects and the p-adic topology on the coefficients and the topology on the Galois group. And okay, so the right notion, which kind of witnesses that we have taken an inverse limit on the left-hand side, is to consider continuous representations. And I want to briefly explain how this works, right? Because the idea is we just, first of all, copy the definition from complex geometry, and then we think about what we have done. Okay, so we take a representation, and then we take the universal cover, we take the constant local system with CP coefficients, and then we quotient out by the anti-diagonal action. Yeah, so far so good, except that we don't know what the universal cover is. Okay, the universal cover of a curve, for example, like for an elliptic curve, was this affine space C, and there's no analog for this immediately in the algebraic world. Okay, so we don't know what to do. And here, perfected spaces come to the rescue. Okay, because they allow us to do the following. So we need to think about, like, if we want to have a replacement of the thing that worked in complex geometry, then like axiomatically, what is it supposed to do? It's supposed to give me a cover of my space, which is a torsor under the fundamental group, so that I can use representations as descent data for this thing. And if you think about what this means, then okay, you can just write down what you need to do in the étale world, in the p-adic world. Okay, and you define it as something which looks horrible from the point of view of schemes. I mean, you take an inverse limit over all the connected finite étale covers of this variety. Okay, so like if you start with an elliptic curve, then this would be the tower of all multiplication maps over this elliptic curve. And if you start with the curve of higher genus, it would be something very infinite and hard to grasp somehow. Okay, so this is some really infinite space. This is called the pro-étale universal cover, and essentially by definition, it is a torsor under the étale fundamental group. Like this is essentially the definition of what the étale fundamental group is. I wasn't very careful about base points. Okay, whatever. There's a way to make this precise. And the fun fact is now that if we are in genus greater than 1 or greater equal 1, so if we exclude a projective space and X is a curve, then this horrible thing there turns out to be actually a very nice thing, namely it's a perfectoid space. Okay, and this is, in some sense, the prototypical way of how perfectoid spaces appear in p-adic geometry. They are also already in the world of Faltings, and even if you want in the world works of Tate, these things appear as infinite covers of arithmetic objects, like, for example, smooth projective curves. Okay, and maybe this gives some motivation for why testing the space by perfectoid spaces could be a good idea, because you see these universal covers like this X tilde thing there. Okay, so that's maybe one thing to take away from this from this world of local systems, that one can understand them in terms of these perfectoid spaces which cover the variety. And in particular, this also tells us now what to do in the final world of the final cohomology theory that we talked about, namely v-cohomology. This was by design about understanding X in terms of perfectoid spaces, and the correct notion of coefficients for v-cohomology is now that of a v-vector bundle. So what is this? This is essentially just a vector bundle on the v side, namely it's a finite locally free sheaf on the side of perfectoid spaces over X, and this naturally has a structure sheaf. So it's a module over the structure sheaf. And if we just allow this universal cover to exist, yeah, if we admit this as a concept, then this gives an easy way to say equivalently what a v-vector bundle is, namely it's just a usual vector bundle, whatever that means, on this space X tilde, together with a descent datum along this universal cover. Okay, and then I can define my generalized cohomology theory, which is v-cohomology, with coefficients in a v-vector bundle, and it's just the internal cohomology of this side. And if I take the trivial vector bundle, this recovers the v-cohomology from earlier. Okay, so in some sense, the definition is always very easy in the v-topology. It's the side which is a little bit scary. Okay, and we wanted to explain what p-adic non-abelian Hodge theory is with this little detour through perfectoid spaces. Okay, and the point should now, of course, be that we can somehow match up coefficient systems and then compare cohomology. Okay, and this is what I want to do now. So let once again x0 be a smooth projective variety over QP or QP bar, and then I take X to be the base change to CP. This is the setup of this p-adic Hodge theory I'm talking about. Okay, and The theorem which explains how to match up these coefficient systems is called the p-adic Simpson correspondence. Really, it should be called the p-adic Collette-Simpson correspondence because it's a p-adic version of the theorem of Collette and Simpson, but I don't know what happened historically. The first article in this thing was called p-adic Simpson, and the name has stuck ever since. Not my fault. Anyway, and okay, so this has a long history. Many people have worked on this, and the perspective I present in this talk is one that I learned from Abesse and Gros. But so the theorem I present here is due to Faltings, one of the first works in the area in 2005 for curves. And then 2 years ago, I explained how to generalize this to higher dimension. And the statement is that once again, we can match up coefficient systems. Okay, we have on the one hand, V vector bundles, these coefficients for V cohomology. And on the other hand, Higgs bundles, which are the coefficient systems for Hodge cohomology. Okay, so this matches up 2 of these worlds. But there was a third one, namely local systems. How do they fit into the picture? Well, it turns out that local systems sit as a subcategory in the category of V vector bundles. Okay, but they are not all V vector bundles. Okay, and this functor from CP local systems to V vector bundles is actually easy to describe. It looks like a Riemann-Hilbert functor. Okay, you take a local systems and you just tensor it with a structure sheaf. And because both of these are somehow in some sense trivialized by the universal cover, you know that this will define a V vector bundle. And then it's this functor S, the p-adic Simpson functor, which, like the Collette-Simpson functor, is a bit impossible to write down explicitly. Well, I mean, well, it is possible, but not on the slide. Okay, so that's maybe a bit odd on first sight, because in complex geometry we could somehow match up everything. And now there's an inclusion. And the reason is that compared to the Collette-Simpson correspondence, Faltings has kind of overperformed, right? He wasn't supposed to match up all Higgs bundles, but only the ones which are semi-stable of degree 0. Yeah, that's the category that came up in the complex Collette-Simpson correspondence. And for whatever reason, in the p-adic world, we see more. We can match up all Higgs bundles with all V vector bundles. And if we then care about local systems or representations of the fundamental group, then instead we land in this category of Higgs bundles, which are semi-stable of degree 0, the same category as we have in the complex world. And yeah, I mean, wouldn't it be nice if the world was exactly as in complex geometry, namely that this was actually an equivalence? And this is something that Faltings asks in his article. And this is expected to be a very hard question. So it's still open whether CP local systems correspond exactly to the Higgs bundles, which are semi-stable of degree 0. At least in the case of curves. In higher dimension, I need to say something about Chern classes, but we can also write down a concrete expectation. Okay, so that's a cool open question we have in the area. Anyway, but we wanted to compare cohomology, right? So now that we know how to match up coefficient systems, we can again compare cohomology. And this works out perfectly fine. So if we start with a local system and then take its associated V vector bundle and the associated Higgs bundle, then all the various cohomology theories agree. Yeah, and once again, you could now extract from this some cool versions of Eichler-Shimura isomorphisms if you wanted to, for example. But okay, even if I take the trivial local system, this is really a generalization of the Hodge-Tate decomposition, yeah, which was this theorem that we maybe know and love for number theoretic applications. Okay, and okay, this I want to be brief about. I said that there was some fancy stuff going on in complex geometry about moduli spaces, and of course we wanted to do the same stuff. And it actually works out surprisingly well, at least if X is a curve. So this is joint work with Dash and Ju from last year. The first statement is there are reasonable moduli spaces, okay, for V vector bundles, Higgs bundles, local systems, representations, all these kinds of things. And okay, if you say enough technical words, then these are actually represented by nice varieties even. And there was this inclusion of the category of local systems into the category of V vector bundles, and this I can geometrize as an open immersion of varieties. And then there was this equivalence between V vector bundles and Higgs bundles, and this turns out to be surprisingly subtle. It's not an equivalence of varieties or of stacks or anything, but one can prove that one is really an étale twist of the other. This is something which doesn't really have an analog in the complex world. This is just a feature of p-adic geometry. So that's kind of cool. Okay, in the very end, I want to say a word about an application of this theorem. But okay, I just wanted to mention this briefly that, okay, one can actually talk about moduli spaces. And I think this is a very interesting direction for the future. Okay, but I talked about complex Hodge theory for a long time, right? But this is an arithmetic conference. So I want to now actually say something more precise than just mumbling Eichler-Shimura every once in a while. Okay, and the first application, I want to discuss two applications of this whole theory, okay? Sample applications if you want. And the first one is supposed to be about Zen theory. So this is a classical topic in p-adic geometry. And it's about classifying or like describing, understanding, studying the semilinear continuous representations of the absolute Galois group of QP on finite dimensional CP vector spaces. For example, how this comes up in practice is that you have a p-adic Galois representation, because that's what you do in life, or because you study modularity or whatever, and then you tensor it up with CP, and then endow it with the diagonal action, and then you get such a thing, such a continuous semilinear representation. I mean, semilinear just means that they already have a non-trivial action on the coefficients, right? And it's supposed to respect that. And okay, classically, one can use this to define, for example, Hodge-Tate weights. Okay, and there's a theorem of Zen in a very nice paper from, or a series of papers from the 1980s. And I want to, okay, he has a very precise theorem, okay? But it's not usually what people remember about this thing. So instead I want to state it in the way that I would have remembered it until 3 years ago, okay? And I think many people do the same, which is that these things are sort of equivalent to Zen modules. Okay, so these semilinear continuous representations are some of the difficult things. They come maybe from something like p-adic representations on QP vector spaces that we want to understand. And then there's Zen modules, which are much easier. Namely, they are simply finite dimensional QP vector spaces. Okay, those we can understand. And then there's just an endomorphism on this vector space. Okay? But the thing is, they aren't actually equivalent. Like, Zen proves they are not. It's just that, I don't know. Okay, so the precise version of how I remembered it is, okay, they are not actually really equivalent, only kind of closely related, maybe after passing to a finite extension or whatever, or sometimes after an infinite amount of choices, and I don't know. It's really complicated, but in practice, you can usually kind of assume that you can go from one side to the other, okay? But there's something to be careful about. And okay, when writing papers, you might or might not be careful about this. Okay, and the point is that using non-abelian Hodge theory, and in particular using moduli spaces, we can make sense of all this waffle and say precisely what's difficult about this identification. Okay? So how does this work? The idea is we use not the hard results from non-abelian Hodge theory, but the perspective and the things we learned about it from first the complex geometry and then the p-adic geometry. And we do a conceptual leap where we replace the smooth projective curve by the point spar of QP. And the idea is that as far as cohomology is concerned, these two things behave in some sense similarly. In some sense, they have cohomological dimension 1, etc. Okay, and okay, that may sound like bullshit, so let me substantiate this a bit more. I talked about this universal cover, which was supposed to be an analog of the universal cover in complex geometry, right? And I can just copy the same definition for spar QP and see what it gives me, okay? So it's supposed to be the limit over all finite étale connected covers. Okay, so this is just some fancy algebraic geometry way of saying that I take the limit over all finite extensions of QP, okay? So now we are finally doing really number theory, okay? And I take the limit of those guys in some p-adic category, which means that I automatically perform some kind of completion, which is why this limit is really the same thing as spar of CP. Okay, so spar CP is the universal cover of spar QP. And the important point is now that I can reinterpret what these semilinear continuous representations are, namely they are precisely the descent data for vector bundles along this morphism. Okay, one can argue that all V vector bundles on spar CP are trivial. Okay, I mean, too complicated way of saying this is that this is the dimension 0 case of the p-adic Simpson correspondence. Yeah, they are the Higgs bundles on the point, and those are trivial. Okay, that was a bit stupid. Anyway, so any V vector bundle on spar CP becomes trivial. And for this reason, if I think about what this continuous representation up there is, it's really a co-cycle. And co-cycles define descent data. Okay, so these things are what Zen is studying in his article, we can reinterpret as being exactly the category of V-vector bundles. And the fun thing is now, oh, okay, so that's what I just said, yeah? So these continuous semilinear representations are precisely the V-vector bundles. And the fun thing is now that Zen modules are in this context really the analogs of Higgs bundles. Okay, I can give a cohomological definition of what a Higgs bundle is, and then if I think about what I need to replace the differentials by, I get the structure sheaf, and then if I just write down, like without thinking about anything else, the definition of a Higgs bundle on SparkUP, I get a Zen module. Okay, so the point of this is that what Zen is doing in this article from this perspective of the p-adic Simpson correspondence is really proving a kind of p-adic Simpson statement, proving that V-vector bundles are in some way equivalent to Higgs bundles. Except that not really for some reason, they are only kind of equivalent. And this we can now explain. Namely, this perspective yields a new moduli theoretic perspective on Zen theory. And okay, so this is joint work with Eugen Hellmann, and I don't think we'll finish it this year, but okay, so we have already written up the proof of the theorem, so I think I'm allowed to talk about it. Okay. And the statement is that one can once again define moduli spaces, like we did for the p-adic Simpson correspondence. And this moduli space of V-vector bundles, or moduli stack, turns out to be an étale twist of the stack of Zen modules. Okay, so this makes geometrically precise the idea that the two are kind of closely related and sort of locally equivalent or whatever, maybe after some infinite amount of choices, but not actually, okay, because there's a twist. And for example, this infinite amount of choices that you read about in articles of Fontaine, for example, is about trivializing this twist in certain situations. Yeah? So this really, in my opinion, gives a geometric interpretation of what the subtlety in Zen theory is. And okay, so the reason we have some concrete applications of this for the categorification of the p-adic local length program. Okay, and then maybe just very, very briefly, I want to talk about a second application, which is joint work in progress with Magnus Carlsen and Ruth Wild, my colleagues in Frankfurt. And the idea is to apply non-abelian Hodge theory to n-abelian geometry. Okay, and if you just read these two topics, then you might be like, so you're telling me that two topics which have basically the same name, right? A non-abelian Hodge theory and n-abelian geometry have something to do with each other, right? No shit. Okay, but it's really not so obvious at all. And okay, so I'm quite excited about this. So I just want to very, very briefly sketch the main idea of this without giving any details. So what is non-abelian geometry about? N-abelian geometry is about, okay, so let's say we're in the setting of hyperbolic curves of a QP. And one question on abelian geometry, in some sense, asked by Goethe and to Faltings, is to reconstruct this curve from just the datum of its étale fundamental group. Okay, so does the étale fundamental group know everything about the curve in some sense? And okay, why should non-abelian Hodge theory have anything? Okay, so first of all, the answer to this question is known. Yeah, Mochizuki proved in the 90s that this is in some sense possible. Okay, but we can now give a new some approach to this, which is that, okay, so very roughly, the idea is what the étale fundamental group determines is really the stack of local systems, okay? Because in some sense, this is just a stack of representations of this fundamental group. So if you know about the representations, if you know about the group, then you know about its representations. And therefore, you know about this moduli space of local systems. And because we know something about moduli spaces in p-adic non-abelian Hodge theory, we can explain or make precise the idea that this moduli space determines the Hodge moduli space. Okay, but this is an object which is very well known especially in complex geometry, and it's known that this space determines the variety. And okay, this last step is actually really easy. You use the Hitchin vibration in some way. Okay, so this gives a concrete new way to reconstruct X in some sense out of the fundamental group. Okay, but this is work in progress. I just wanted to mention that yes, so these are some things one can do. Okay, thanks very much.